Hi, everybody. This is Mr. Folly, and welcome to Podcast 5.1, where we're going to learn about covalent bonds and how we will share our valence electrons here. So, which is going to be why bonds form. We talked a little bit about metallic and ionic before, and now we're focusing on covalent. What happens to them? What type of elements are in these bonds? How electronegativity can help us determine polar covalent or non-polar covalent? And describe the difference of properties, which we're going to focus on there. And name and write the formulae of molecular compounds. So let's hop to it. Covalent bonds. So, covalent, co means share. And valence means your outer electrons. So they're sharing their valence electrons. How nice. So it's made of two non-metals because those are the types of things that share instead of transfer. These are directional covalent bonds, meaning if I have X and Y and they share, that's only between those two. So, like, I share my house with my wife and kids and nobody else, just those people. I don't let strangers come wander into my house and stay there. And they share to fill their octet, because remember, full equals low energy, which equals stable. And when you fill the octet, let me tell you what double counts like your house means. If I asked you, do you have a house? You would say yes. If I asked your parents, they have a house? They would say yes. If I asked your brothers and sisters, they have a house? They'd say yes. So does that mean there's three houses? No, there's just one house, but it counts for each of you. So for example, NH3, with the Lewis dots we learned before, if I have H's here, remember nitrogen needs 8 valence electrons to be full and stable. And hydrogen only needs 2 because it's way up on top. Remember, hydrogen and helium are way up here, and they only need 2. So notice here, there's 2 electrons in a bond, so hydrogen right here is happy, it has 2. This hydrogen's happy, it has 2. This hydrogen's happy, it has 2. But nitrogen, I'm going to go crazy with my color, which is tough for a colorblind guy, has 2, 4, 6, 8. So notice how those bonded electrons count for both nitrogen and hydrogen. So it's sharing them and counts them both. Ionic to covalent is a continuum. So that means there's not this huge jump of differences that screams out to us like happens in some other things. So the difference, if there's no difference in electronegativity, no meaning pretty much no significant difference, it's nonpolar, and that's 0 to 0.4. If there's some difference, it's polar, and the word polar means ended. So what this means is one end is going to be a little bit positive, and the other end is going to be a little bit negative. So polar means ended, like the North Pole is one end of the world and the South Pole is the other. If there's lots of difference, it's ionic, so it's like superpolar. Okay, that's 2.0 and up. So being a continuum is just like looks. Everyone falls somewhere in the scale from ugly, like this dog with its bagged with face, to regular, no one's more regular looking than Tom Hanks, to beautimous. Yeah, she is beautimous. Woo! Hello, June Boo Boo. So again, this is just an application of it. These are the same scale we talked about before. So what is N to O? N is 3.0, O is 3.5. If the difference is 0.5, that's polar. Notice most things that are different are polar. What is F to F? That's 4 minus 4, which is going to be nothing. So that's going to be nonpolar. Nonpolar. And remember, polar is polar covalent, and nonpolar is nonpolar covalent. Lead to F, lead is 1.8, F is 4.0, so that is 2.2, which is ionic. C to H, I forgot to put H in here, H is 2.1, so C to H is 0.4, and remember, C to H is nonpolar, and it is quite rare that different elements have nonpolar covalent bonds, but C to H is one you should know. And we're going to talk about nonpolar covalent bonds. Nonpolar covalent bonds occur between two metals. For a nonpolar covalent bond, electrons are shared evenly, all like the little crackers being shared by little rat 1 and little rat 2. Okay. They're mostly diatomic elements, or C to H. There are other times the electronegativity difference tells us, but pretty much it's C to H, or if they're diatomics. They have the lowest boiling point and melting point. You should write that down if you don't want BP and MPR. And it never conducts electricity. Remember, electricity is a flow of ions, and it doesn't have any ions. They're poor heat conductors, and they don't dissolve in water. So nonpolar covalent never dissolve in water. Polar covalent bonds are two metals, mostly. Sometimes there's a metal and a nonmetal that sneak in there. And a polar covalent bond has uneven sharing. Remember, polar means ended. The atom with a higher electronegativity will have a slight negative charge. The other atom will have a slight positive charge. Okay, so it's kind of like a battle for these electrons, and it gets to decide where it's going to be. So my analogy for this is, say that Dino and I share a dog. Here's Dino, here's me, and here's our dog. Woof, woof. Give it some whiskers. Okay. Now, Dino and I share a dog, and for the dog between Dino and me, the dog, of course, likes me better than Dino. So if we both show up at the same place, the dog, I forgot to draw out legs, rolls over to me and, goes, "Roof, roof, roof, roof," and wants me to pet it because it loves me, and I'm such a great person that likes me better. Now, if I'm not there, and Dino's with the dog will roll over to Dino and say, "Oh, scratch me behind the ears, you're all right." But it likes me better. So if the dog has a choice, it's going to spend 90% of its time with me and only 10% of its time with Dino. So it's an unbalanced sharing. Okay. So a molecule in uneven distribution is said to have a dipole. Di means two, pole means ends. So this delta symbol, it's pronounced delta, represents the partial charge on each side of the molecule as indicated. This symbol right here, boop, boop, the symbol points towards the negative end of the molecule. So if it was me, again, and Dino, I just got shorter, the delta arrow would be pointing towards me because the electron, dog, spends more time with me. And the positive end would be Dino, it's missing it. And polar covalent bonds dissolve in water. So if I have an N to O bond, from the electronegativity chart before, oxygen was 3.5, nitrogen was 3.0. So if I were to draw an arrow, my arrow would be pointing towards oxygen. If I were to put my deltas, oxygen's a little bit negative, so it's delta negative, and nitrogen's delta positive, because the electron stays around here a little bit more. And if the electron's around here a little bit more, it comes over here a little bit, but it's over here most of the time, it's going to be a little bit negative over here. So what type of bond is made of two metals? Aha, I tricked you. I've been talking covalent, but it's metallic. Conducts as a solid. That's only metallic. Has a low melting point. That would be nonpolar covalent or polar covalent. Okay. Some metals too. Really, one metal. Some metal. Has an electronegativity difference of 2.2. That's an ionic bond. Remember those differences you just wrote down. 0.2, that's less than 0.4, so that's nonpolar covalent. Transfers electrons, that was ionic. Shares electrons evenly. If it shares evenly, polar means ended, so it's going to be nonpolar covalent. Has the highest boiling point, that's from the strongest bonds of ionic. Is soluble in water and has a high electronegativity difference. That's ionic, right? So soluble in water, ionic is often soluble in water. And a high electronegativity difference means it's ionic. Soluble in water and a low electronegativity difference would be polar covalent. Naming molecular compounds. Remember, they'll always have two nonmetals. Molecular compounds are covalently bonded. We use prefixes. And most of the prefixes are easy. 1, 2, 3. Now, tetra, that prefix tetra is not something you've never heard of before. Tetris, for example, has every block on Tetris has 4 blocks. Remember, you got the line that's 4 long. Then you got the little L. And then you got the little jiggity jaggedy, who's-ity, what's-ity, right? So those are all the Tetris pieces. And notice they all have 4. By the way, be careful. It is di, not bi. So hexa is 6. Hepta is 7. It is not septa. It's hepta. Octa is 8. Nona is nu. That's 9. And deca is 10. And then the last element has to end in "-ide" and sound good. So we're going to let CO be your guide. So to let carbon monoxide be your guide, there's no mono on the first one. CO is carbon, you can almost spell it, monoxide. And you've seen that before, right? There's no double O, so it is not carbon monoxide, although I wish it was because that would be way more fun to say. Like I want to stop saying hurricane, start saying hurricane. Hurricane Sandy. So that's wrong. And then we'll just do a bunch of them. SF6. Sulfur. Notice I don't put the mono on it. Hexa, fluoride, U-O-R-I-D-E. Notice the ide is on the first one, not ide. Pickle 5 is phosphorus, not mono. Pentachloride. Xenon 2, so if I have a prefix of 2, I need my prefix. Dixenon. Octabromide. That's water, just to keep you on your toes. Trinitrogen monosulfide would be, trinitrogen means N3, mono means 1, S. So I do use mono, but only in the second one. Hexasulfur, sulfur, hexa means 6, dichloride, chloride, 2. Decanitrogen, N10, monoxide, O. Sodium dihydrogen phosphate. Hey, wait a minute. Sodium's a metal. If it starts with a metal, you write the ions, Na positive. Dihydrogen phosphate. Oh, that's mean. That's an ion you didn't have to learn. H2PO4 negative. Ooh, look at that, Mr. Fowler. Give me fancy pants ions. Don't you feel smart? I do feel smart. Thank you. Sorry to give you an ion you didn't have to memorize. But that's phosphate, and dihydrogen phosphate kind of plays along. Do not reduce moleculars. Molecular compounds are the exact formulas. Ionic compounds are already reduced. So if you change the molecular formula, reducing changes their identity. So the elements in DNA are just CHOS. So you wouldn't say, oh, what's your DNA? It's just CHOS. And you know your DNA is the whole crooked ladder of whatever silliness it is, and you've got all those things, and there's special genotypes and phenotypes, and dyad, tri, whatever it is, and codons and all that nonsense. So it matters what these numbers are. Okay? You wouldn't want to reduce it. If you reduce it, it will cause a mutation. Not that just you can say, oh, I'm reducing it, but it indicates something different. So, and if you indicate something different for DNA, it messes up what your DNA does, and you won't be able to do chemistry, or think, or breathe. To review. Metallic bonding is made of two metals, non-directional valence electron sharing, conducts in solid and liquid, that's hard to read, variable melting point, it's insoluble, and variable strength. Covalent bonding, hey, this is new. Two nonmetals, valence electrons are shared, but only between two atoms. It never conducts electricity, it has a low melting point, it is only polar covalent is soluble, and they're the lowest strength. Ionic bonding, metal and nonmetal, valence electrons transfer, right? Jump from one to the other. Conducts as a liquid or aqueous only. Has the highest melting point. Most, but not all, are soluble. And they're highest in strength. So, with all that joy and all that wonderful bit of learning about covalent bonding, you finally get to hear